This is part 5 of carbohydrates, and in this part, we are going to see configuration of D-glucose from D-Arabinose and objections against open chain structure of D-glucose. So, first of all, configuration of D-glucose from D-Arabinose. The open chain structure of glucose contain four different asymmetric carbon atoms. So first of all, what is asymmetric carbon atom? The carbon atom which is attached to four different groups or atoms on four sides. That is known as asymmetric carbon or chiral carbon, asymmetric center or chiral center. And glucose has four chiral centers or four asymmetric centers. This is the structure of glucose. So here 1, 2, 3 and 4. These are the four asymmetric carbon atoms because this aldehyde is not asymmetric and this CH2OH is also not asymmetric. Therefore, the number of possible stereoisomeric structures would be and number of possible total number of possible stereoisomeric structures are given by the formula 2 raised to n, and this n is nothing but number of asymmetric carbon atoms. So here 2 raised to 4, it becomes 16, and here 2 raised to n, 2 raised to 4 becomes 16, that is 8 pairs of enantiomers. 16 isomers, that means 8 pairs of enantiomers are possible, and the naturally occurring dextrorotatory glucose is represented as D plus glucose. Out of 16 stereoisomers, only one configuration represents D plus glucose, and out of 16, only one structure is there which represents D plus glucose. So the configuration of D-glucose defines the arrangement of hydrogen and hydroxide, that is H and OH groups on carbon atoms 2, 3, 4 and 5. It is determined on the basis of known configuration of D-Arabinose. And the D-Arabinose has the following configuration. This is the structure of D-Arabinose where aldehyde functional group is there on second carbon OH, H, third HOH, fourth HOH, and fifth CH2OH. So this is 1, 2, 3, 4, 5 aldo pentose. So from this aldo pentose, the specific name is D-Arabinose. From this D-Arabinose, we can define the structure of glucose. And the following steps are involved in determination of configuration of D-glucose from D-Arabinose. When D-Arabinose is subjected to Kiliani synthesis, it gives a mixture of aldohexose second and third. Here, this is the structure of D-Arabinose. So this D-Arabinose, when it is subjected to Kiliani synthesis, we know Kiliani synthesis is nothing but it is the reaction of increasing one carbon atom in the reactant, and as this is aldopentose, it is converted into aldohexose, and we get two structures, second and third. So this aldohexose two structures are there, and this the carbon atom which is shown in the square rectangle, it is the increased carbon or added carbon. Now the question is to decide whether this second is D-glucose or third is D-glucose. Hmm. And these two on Kiliani synthesis gives to aldoheptoses. Further, when we do Kiliani synthesis with this second and third, we get aldoheptoses. So second on Kiliani synthesis, we get two aldoheptones, this fourth and fifth, and when third is subjected to further Kiliani synthesis, that means increasing one more carbon in the structure, we get sixth and seventh structure. So why we are getting pair of isomers? Because we are increasing one carbon atom, and it may have either OH on the right side or OH on the left side. These two possibilities are there. All remaining structure is same. So there are two isomers, and this is known as enantiomers. So one pair of enantiomers or two isomers we get when we subject any molecule to Kiliani synthesis. So this second gives fourth and fifth, and third gives sixth and seventh molecules after Kiliani synthesis. However, when the aldoheptoses, that is 4 and 5th, obtained from aldohexose second, on oxidation gives two dibasic acids. These are two dibasic acids, 8th and 9th. Why it is dibasic? 1 and 2 acid functionalities, carboxylic acid functionalities are there in both the structures. So these are dibasic acids. So when we get 8th and 9th from second, we from second structure we got 4th and 5th, and from 4th and 5th we got 8th and 9th. Out of these two dibasic, ninth is optically active and other dibasic, eighth is optically inactive. Here, this is optically inactive, but this one is optically active. Why eighth is optically inactive? Because it has plane of symmetry and it is a meso compound. So, if we draw a plane from this carbon, then we come to know that the structure to this side and structure to this side is mirror images of each other. That means this is the plane of symmetry, and because of this, it is optically inactive. However, aldoheptoses, this sixth and seventh, obtained from aldohexose third, on oxidation gives two dibasic acids. These are also two dibasic acid, that is 10th and 11th, and these both are optically active because there is no any plane that we can draw, the plane of symmetry, and hence both These 10th and 11th are optically active. As glucose on Kiliani synthesis followed by oxidation gives a mixture of dibasic acids out of which one is optically active and another is optically inactive, we can conclude that the structure of glucose is that we come from second. So the structure will be second one and not third, because if the structure of glucose would have been third, then after the Kiliani synthesis and oxidation, we must get two optically active compounds. But this is not the case. After Kiliani synthesis and oxidation of glucose, we get one optically active and one optically inactive compound. So the possibility out of third and second, second is the most correct answer, or the second is the most correct structure of glucose. And the final structure of D-glucose is represented as, so let us number 1, 2, 3, 4, 5, 6. Here 2, 3, 4 and 5 carbons are asymmetric carbons. One is aldehyde and sixth one is CH2OH, that is primary alcohol. And out of these 2, 3, 4, 5, 2 and 4 have hydroxy group on right hand side, and 3, sorry, only 3 third carbon having hydroxy group at left hand side, and all other hydroxy groups are on right hand side. This is the final structure of D-glucose that we come to know up till now. So this can be drawn like this: CHO. So here OH, H, then OH, H, OH, H, OH, H, and here CH2OH. Then let us see objections against open chain structure of D-glucose. So this is the open chain structure of D-glucose. The open chain structure of glucose proposed by Bayer account for most of its properties. However, it fails to explain following points. Point number 1, glucose, although having an aldehyde group, it does not give the Skipp's test for aldehyde. This is one objection. Then, second point, it does not give other characteristic reactions of aldehydes. For example, it does not react with sodium bisulfite and ammonia. Third point, glucose pentacetate does not react with hydroxylamine, that is NH2OH, to form oxime. This indicates absence of free CHO or free aldehyde group in the structure. Fourth point, the glucose on treatment with methanol in presence of dilute HCl, that is hydrochloric acid, does not give acetal as expected for aldehydes, but gives two isomeric monomethyl derivatives, that is methyl glycosides. The formation of acetal in case of aldehyde is explained in the following way. This aldehyde, when react with methanol in presence of acid HCl, it is also represented as H plus. It gives H plus, and aldehyde on reaction with methanol in presence of acid gives hemiacetal. Further, same reaction proceeds to acetal. However, in case of glucose, two methyl glucosides are obtained that is methyl alpha D glucoside and methyl beta D glucoside. That is D plus glucose on reaction with methanol in presence of acid gives two glucosides, alpha D glucoside and beta D glucoside. These glucosides do not reduce failing solution and do not react with hydroxyl amine or HCN, that is hydrogen cyanide. This indicates that glucoside do not have free THO group. That is, it does not have free aldehyde group. And last, that is fifth point, D plus glucose exists in two isomeric forms known as alpha and beta D glucose. They have different specific rotation. Alpha D plus glucose have specific rotation 112 degree and beta D plus glucose have plus 19 degree. And equilibrium mixture of alpha D plus glucose and beta D plus glucose have the specific rotation of plus 52.7 degree. If either of two forms is dissolved in water and then the specific rotation gradually reaches 52.7 degree, this change in specific rotation of an optically active compound is known as mutarotation. The open chain structure of D-glucose does not account for this behavior. So mutarotation is the behavior which cannot be explained with the help of open chain structure of D-glucose. These are the some objections on open chain structure of D-glucose. Thank you.